Good morning, everyone, and welcome to another Guideline Geo webinar. Today, we are here to talk about the new ABEM Terrameter VES and VES Max, our current lineup of VES instruments that we launched during the summer of this year, 2023. During the presentation, we'll start with a brief introduction to the company, myself, the VES method and the instruments. Then we'll look in a bit more detail at the Terrameter VES, then the VES Max, then we'll look at the accessories that are available for them, and then I'll do a quick demo of the user interface so that you can see how we would do a measurement with these instruments. Once I've done that, we'll have a look at how you might decide which instrument is right for your needs. And then after that, I'll answer any questions that have come up during the session. So as I said, we start with a brief introduction. Not everyone will know who Guideline Geo are. We manufacture geophysics equipment. We do that under two brands, ABEM and Marlow. ABEM are manufacturing seismic, resistivity, and time domain electromagnetic systems, and Marlow are manufacturing the ground penetrating radar systems. We've been around for quite a while. ABEM was founded in 1923, which means that this is a very big year for us. It's our 100-year anniversary, so you'll see lots of these 100-year logos spotted around the place. And all of our products are made in Sweden. So our factory is in the town of Marlow in northern Sweden. We have a research and development office also in northern Sweden in Umeå, and our head office is in Stockholm. But we actually have offices, 6 main offices around the world, and staff on 5 continents. We've got a distributor network that covers about 80 countries, so we like to think that we're pretty local to most people. And for us, collaboration is a big thing. We like to work with industry partners and academic partners. We find that brings a lot of benefits to us in our product development and understanding sort of where the industry is going. Myself, my name's Jimmy Adcock. I am the product manager for ABEM. I've been with Guideline Geo since 2015. Started as an application engineer doing sales and technical support training, and then moved on to the product manager role a couple of years ago. And I look after the ABEM products. So today we're here to talk about the VES lineup, which now comprises of the Terrameter VES. This is now our entry-level resistivity meter. This replaces the old SAS 1000 that had been around for a very long time. Very nice instrument, but yeah, had reached retirement age. So this is our entry-level system, but just because it's an entry-level system doesn't mean that it is a basic resistivity instrument. This is an advanced unit, but we like to think that it's quite an affordable one as well. The VES Max is something slightly different. It is a much higher specification instrument, and so therefore it is what we would call a bridging unit, and I'll come back to what I mean by that. It has a lot more power, it has better recording circuits, and it has some of our advanced functionality that we don't get in the regular VES system. So let's talk a little bit about what the VES method is, just in case there's anyone here who's just interested in the method as well as the products. Vertical electrical sounding, to give it its full name, is a way for us to estimate how the resistivity changes with depth beneath a single point on the surface of the Earth. It's been around for a very long time, and the extract on the right-hand side of this slide is the first published article about the kind of 4-pin method, written by a gentleman called Frank Venner, and anyone who's been involved with any kind of resistivity measurements will probably recognize the name Venner. And this was published in 1915. So VES has been used for over 100 years. Originally, it was primarily being used for mineral prospection. But then over the time that's changed, and now we see that most of our customers are actually working in groundwater exploration, geological sequencing, and a lot of people are also using the 4-pin method for looking at the earthing properties of the ground at electrical installations on either smaller or larger scales. So for sort of AC installations, you can do quite a small 4-pin survey. For DC methods, you need to go a little bit deeper and perhaps use a system that's a bit bigger, more like the Terrameter. If we were to describe the VES method to someone who hadn't really used it before, we'd say that it's a long established, straightforward method to determine change in electrical resistivity below a single point, and that primarily it's very good at identifying geological layers, looking for the depth to an aquifer, making some kind of estimation as to the quality of that aquifer. Is it likely to be fresh water, or is it more likely that this is salt water that we're looking at, or brackish water, based on the resistivity of that response? We can also use it for sort of identifying broadly where there are large mineral bodies, and as I said, also electrical properties of the ground for these electrical installations. It is a basic method. It just requires 4 electrodes and a resistivity meter at the center of it, but it is a very effective method at determining a resistivity model. If we look at how it works in the field, as I say, we have 4 electrodes, and if you look in the textbooks, they will be labeled A, B, M, and N. A and B are where we will inject current, and so they are sometimes referred to as C1 and C2, current 1, current 2. M and N are our measuring electrodes. They're measuring the voltage of the ground, and voltage is also known as a potential difference, so they are quite often labeled P1 and P2, potential electrode 1, potential electrode 2. When we put our 4 electrodes in the ground, the current is flowing through that volume of earth beneath the electrodes, and we are taking a measurement from a particular point in the middle. And what we say is that there is a focus position, is a place where we assume that the measured value has come from. We assign it to that particular depth. If we want to measure deeper, then what we do is we push those current electrodes further apart, and that then makes the potential field change, and our focus position moves deeper into the ground. So if we repeat that process time and time again, then we can gradually build up this vertical profile of measurement values. Now, there is a downside to pushing those current injectors further apart, and that is that the signal that we can record at the center of our spread with our potential electrodes, M and N, becomes weaker over time. So when the signal becomes too weak, what we can do is we can actually spread the potential pair further apart, and that will boost the signal strength. But we do lose a little bit of contrast. So it's always a balancing act to have M and N close enough that we get good contrast, but far enough apart that we get good signal strength. And the arrangement that we're looking at here is what we would call the Schlumberger array, which is a slightly more efficient way to collect VES than VENA. With VENA, we move all 4 electrodes so they are always equally spaced. So we always have good signal strength because M and N are always moving further and further apart. But it means that we need to move all 4 electrodes every time. Schlumberger array, we can leave the 2 central electrodes in a fixed position for a number of A and B movements, and then just shift them out every now and again just to boost that signal. Once we've gone through that process of gradually moving A and B out, we will then end up with what we call a sounding curve. And so that is apparent depth against apparent resistivity, or pseudo depth against apparent resistivity. And you'll normally see that it's in segments, and each one of those segments is a different MN, or potential pair spacing. In the origins of doing VES survey, we would go from that raw data to a model of ground resistivity by using a set of reference curves, because the problem that we have with that raw data is that it doesn't give us the true resistivity at a particular depth. If you imagine that I'm looking at this focus position, the current has had to flow through all of these layers to get there. It's a very large volume of earth that we're testing when we record the value associated with that focus position. So what we need to do is get back to a point where we have a model of true resistivity values for these different layers. And as I say, originally we would have done that with a set of reference curves, and we would have matched those curves to our sounding. Most people these days will be using inversion software. And this is just a quick description of how inversion software would work. We take our raw sounding curve and we provide that to the software. The software will then create a model of what it thinks the ground might look like in terms of layer thicknesses and resistivities associated with those individual layers. It then repeats the survey that we did. So same current injections, same electrode spacings, and it looks at how the sounding curve would appear if the ground was actually like this model. And pretty much every time, that first attempt will be quite some distance away from the reality of the data that we have provided. So the software will then change the model and through a process of iterations gradually come towards a raw data set from a model that looks like the raw data set from the real world. And at that point, it will stop and present us with that model and say, this is what I think the ground looks like at the site where you were surveying. There are some caveats to that model in that there are a number of different models that can produce the same raw curve. So if you change the layer thickness and the resistivity at the same time of a particular layer, you can actually produce a result that would look very much like the same raw data. So we always need to be aware that when we look at these models, what we're trying to achieve is a good fit between the modeled data and our original data, and also a realistic model, something that fits with our assumptions about the geology on the site that we're working at. So what we always say is that you know, a single measurement on its own won't give you your proper interpretation. You need to use some other data stream, and quite often the first of those alternative data streams is your knowledge of the geology or maybe the hydrology in the region that you're working, so that you can look at the model and say, yes, that's realistic. We think that's probably a fair representation of the site that we're working. Once we've created these 1D models of what we hope is true resistivity against depth, we can go a step further. So we can look at them, we can plot them in their relative 3D space so that we can see how the resistivity is changing through the subsurface across a broader area. We can build 2D profiles out of them, or we could even actually build a 3D block where the construction blocks, the parts of those blocks come from the 1D soundings, and then slice it at different depths to see resistivity maps across the area. So that's the background of the method. So let's now talk more about the instruments themselves. As a lineup, what we're saying about our new VES instruments is that just because you're doing a basic survey method doesn't mean you need to limit yourself to having a basic instrument. So we have been inspired by our proven Terrameter LS and LS2 instrument, and it's that platform that we have built the new VES products on top of to give us a VES system that has improved performance and functionality over the existing product range. The VES itself is, as we say, our entry-level model, but it's been designed to have a better output, more power, better data quality, better receiving circuits, a much nicer user interface to use, and improved ease of use. And we've wrapped that up into the kind of familiar ABEM package of a rugged casing. And we hope we've been able to do that at an affordable price. VES Max, as I said, is something slightly different. This is a bridging instrument. This has much more power, has much better receiver circuits, has some of our advanced technology that is on the Terrameter LS2, but also has some limited imaging capability. It actually would allow us to do small spreads or to be able to switch between electrodes automatically rather than being limited to just using 4 pins that we move manually every time. So this system has a lot more capability. It would be better if you needed to do very deep VES measurements because it has additional power, it has a better receiver circuit, so can differentiate smaller signals. Also better for near surface IP, again, because those receiver circuits are slightly better specification, and that it can put more current into the ground. And when we're doing a shallow IP survey, we really do want to be able to charge ground up, and that requires us to be able to put in more current. So just looking at the technical highlights of the two instruments, I thought I would start by comparing the Terrameter VES against the SAS 1000. So those of you who know the ABEM products, maybe you've used or at least have seen the SAS 1000. As I say, we were selling that in one form or another for about 25 years as our kind of entry-level VES system. So I thought it was fair to, it would only be fair to compare the new Terrameter VES against that product that a lot of people know and have used. So in terms of the survey, the physical survey when we're in the field, we have much better resolution. We can refine much smaller signals. We have a much better output current. And as I say, if you can increase the amount of current that you put into the ground, that will boost the voltage that you're measuring. So you're moving your measurement away from the background noise, improving your signal to noise ratio. So hopefully allow you to produce more reliable data and therefore a better model at the end of the day. The VES also has a built-in GPS in the handle. So that means that every sounding we take is georeferenced. It is located on the ground so that we know exactly where we've taken that sounding without having to do a separate measurement. If we talk about the actual user experience, being on the machine, collecting the data, we have a real-time sounding curve, so we can see our data, and the sounding curve can be quite useful for helping identify bad readings. We would normally expect the sounding curve to be relatively smooth. So if we see it's jumping around a lot, then we might want to look at our settings or our electrode placement and see if we can improve upon them. We also have a much nicer user interface, graphical user interface compared to the old LCD screen that we had on the SAS. And within that is our active guidance that we launched earlier this year, where we have, via a single button press, information and guidance about whatever is active on the screen at that time, whether that's a menu item or a data display or one of the menu setups. Press that single button, up pops the screen, and it'll give you advice. And we like to think that it's a bit like having an application engineer sat next to you. We've got a lot more memory in the machine. Not that that's a huge issue with VES. Don't tend to be collecting vast amounts of data, but it's on a SD card that could be popped out of the instrument. We've got Wi-Fi, Ethernet, and USB connectivity on the instrument, and it also has better operating temperature range. Remains at IP66, so that's dust-proof and sealed against high-pressure water jets. So there isn't really much weather that it's going to be afraid of. And we also have fairly simple remote control of the instrument and the ability to perform remote diagnostics. So if you have any concerns about the operation of the instrument, you can connect it to the internet and one of our engineers can jump on board and have a look at it for you. And we think this is genuinely a really nice gateway product. So if you're just getting into resistivity work, you can start off with a Terrameter VES, and actually it allows you to upgrade that system at a later date to a full imaging system if you want to, and I'll talk about that a little bit later. Again, those of you who are familiar with the ABEM lineup, you might know that we had a VES version of the LS2, and that was really just an LS2 with some of the functionality removed. But we've made some changes to actually make this a much more rounded VES product, a true VES instrument as opposed to that LS2 VES. So we've changed the end panel so that it's much simpler. There's taken out anything that's unnecessary. So we have our 4 connections for our 4 pins, C1, C2, P1, P2. We have our Ethernet connection, USB port, and our memory card. Grounding point for safety, so we can ground the case next to where we're doing the survey. And we have our auxiliary port, and we'll talk about what we can use the auxiliary port for in a later slide. We now have a fully reviewable table of results, so you can go back and see all of the measurements you've taken, compare them side by side, look for any trends, look at the data quality, review the quality of the measurements, and so that's all in there. We also allow you to make your own custom VES spreads on the instrument. So it comes preloaded with Venner, Schlumberger, a couple of other preloaded VES protocols, but everyone has their favorite recipe for a VES measurement. And so you can enter your preferred electrode spacings and save those to a list. So next time you come to use the instrument, there they are ready to go. And you can just set it up and it will give you that list to work your way through. We've changed the layout of the menu. So anyone who's used the Terrameter LS will kind of recognize the menus, look at the look and feel of this, but we've made it so that now the window that you land on to begin the measurement is at the center. And then if you move in one direction, you have all the VES pages. And if you move in the other direction, you get live results and also imaging pages, because we can actually use this instrument with an external switch box to do imaging. And I'll talk about that a little bit later. So that's the VES. I also said that we have the VES Max, and this is actually the new name for what was the Terrameter LS2 VES. And as I say, this is a much more powerful instrument. So it has 150% more current than the old SAS 1000, and also 2/3 more current output than the VES. We have also a much higher output voltage, and that's important for being able to push against the ground resistance. That's the big thing that is going to limit the amount of current we can get into the ground, is the resistance of the ground. And the higher our driving voltage, the more current we'll be able to put in. So if we want to drive deeper, then the VES Max is the answer for us there. As I said, it does actually have some limited switching. So we can have 16 electrodes attached that we can switch between automatically for taking measurements or injecting current. And it has 2 measurement channels, so we can take 2 voltage readings at a time, whereas with the VES, it's limited to just a single channel like the old SAS 1000 was. We also have some of our advanced functionality. So we have the full waveform recording. So rather than just what is the average voltage recorded during a measurement cycle, we can see how the voltage changes over time. We can also look at how the input current changed over time, so that we can see everything that the instrument has done. That can be very useful as a teaching aid, as a diagnostics tool, and also for very advanced IP work. We can do full waveform IP studies. We also, on the subject of IP, have our 100% duty cycle mode, which is where in a traditional IP survey, you inject current, measure the resistivity at that point, you then switch the current off, and you look at how the voltage in the ground decays over time. So you have an on period and an off period, and that off period means that your measurement takes you at least twice as long to achieve. With the 100% duty cycle, we don't actually need to switch the current off. So we can switch from a positive current pulse to a negative, measure the resistivity on both of those pulses, and in between, while we're doing the changeover, we can measure the IP effect. So speeds up the survey, also produces a better signal to noise ratio as we're measuring the effect from a positive pulse to a negative, rather than from a positive to 0 or from a negative up to 0. So we said that the VES Max can do some basic imaging. Obviously, 16 electrodes isn't very many. You're not going to be doing a huge amount of ERT with just 16 electrodes available to you. But one thing that it can do is it can make your VES measurements a little bit more efficient. And so what you could do is that you could have 16 potential electrodes laid out, 8 different pairs at different spacings, and they could be permanently attached to the instrument. And then we would only need to move the current electrodes out. And every time we move the current electrodes, we can measure from all of those potential pairs. Then when we come back to the office at the end of the day, we have a selection of voltage pairs to choose from. So when I talked earlier about this balancing act of being able to pick a potential pair that has good contrast, but also good signal strength, we don't need to think about it while we're in the field because we will have collected all of them at the same time. And then we can pick the best one for each current separation from the list that we have available to us. So sort of takes out some of the worry that you might be collecting data that is less than perfect whilst you're in the field. So let's now have a look at the instrument sort of system as opposed to just the central resistivity meter. So a VES measurement, as we say, is a pretty simple set of equipment. It's the resistivity meter, 4 cable drums, 2 for current, 2 for potential, some electrodes, some cables to jump between them, and some clips to attach. And then at the end, we would have some kind of processing software for us to be able to go from those raw sounding curves to a resistivity model of the ground. So the accessories that we have are, as I say, the VES cable set, and the standard cable set has current cable drums that are 750 meters long, potential 250 meters. So that allows you to have a Schlumberger layout with a 1.5 kilometer separation between your current electrodes, which would equate to somewhere around 300 meters depth, just a little bit less. The VES instrument, we sell that in the same way that we sold the SAS 1000. So it doesn't come as standard with an internal battery or a power supply to run it in the office. It's designed just to be used from an external battery, exactly the same as the SAS 1000 was. However, we have internal battery packs that you can put in it, and they'll allow you to do a small number of VES measurements, and an office power supply that lets you work on the machine, set up VES measurements, download data while you're in the office without having to have an external power pack. That office power supply will also charge the internal battery. If you buy a VES Max, those come as standard. For the VES or the VES Max, we also have an external power adapter. We launched this year. This allows us to run the instrument from a generator. So if you are on a long field campaign where perhaps recharging batteries at the end of the day is problematic, then cut out taking the battery into the field and a charging unit. Just take one of these small suitcase generators, only needs to be 600-700 watts, and you can then run the instrument via the power adapter. It gives a nice stable 12 volts, even if the instrument is trying to pull 30 amps on that 12 volt side. The VES comes in a wooden shipping crate, a nice sturdy wooden shipping crate. The VES Max comes in like a Pelly style plastic flight case with wheels and a handle. So if you're buying the VES and you would prefer to have this slightly easier to maneuver plastic casing, then you can buy that as an accessory. We have non-polarizing electrodes, particularly good if you want to do SP, spontaneous potential measurements, where you measure just the natural voltage in the ground, or do IP with better data quality. You can use these non-polarizing electrodes where you don't need to use a full metallic electrode that can cause SP effects. We also have our log 300. This allows us to take resistivity and IP measurements in water-filled boreholes, and that plugs into that accessory socket, auxiliary socket on the end panel of both the VES and the VES Max. And that allows us to do resistivity and IP logging to a depth of 300 meters. We also have the external selector box, our ES1064, not the catchiest of names, but that allows us to do ERT with the VES or the VES Max, full ERT layouts. So each one of these allows us to have 64 active electrodes, or if we're using our extended cable set, a 2D 81 electrode spread. It also means that if you are an existing customer with a SAS unit and you have an ES1064 already, if you were to buy a Terrameter VES and drop that into the system in place of the SAS 1000, it would work. Connections and communication we've kept the same, we've maintained that, so that any existing ES1064 unit would still work with your new VES product. We can daisy chain these as well, so we're not limited to just one. We can add another 64 electrodes by adding another box, and we just keep adding those on and on. Then, of course, we have the software options, and as a minimum, we would take one of the 1D inversion software packages, either in Interpex IX1D or Aarhus Spear DC, and that allows us to go from that raw data to the resistivity model. And optionally, we could also include Aarhus Workbench from the Sequent family of software, which then allows us to do those sort of extra steps where we move from just a 1D model to being able to view them in 3D space, make 2D profiles, or generate a 3D volume that we can then slice horizontally. It allows us also to deal with other geophysical data sets. It allows us to bring in aerial mapping and other sort of GIS type layers as well. I talked a little bit earlier about the fact that the VES is a kind of gateway product and that you can actually upgrade them. So the ABEM Terrameter VES can be upgraded to a VES Max. Unlike our imaging systems, though, that upgrade does require it to come back to a Guideline Geo Service Center in order to have extra hardware put in it, but you can upgrade from one to the other. The VES and the VES Max can be upgraded to an LS, to the imaging system, the ERT system. Again, by sending it back into us, we can put the necessary hardware into the box for that to be a full imaging system. And it's, as I say, yeah, it's a physical upgrade rather than just a change of the license. However, once you've made that upgrade to an LS2, and you are on the ladder, so to speak, even if it's the basic LS2, then you can upgrade to other LS2 models in the range simply by changing the license code. So at that point, if your requirements change over time, you want more measurement channels, you want more power, whatever it might be, you can do that just by a license upgrade. So the instrument doesn't need to come back to us. So once you're on the LS2 ladder, things become a little bit simpler. So those are the products, those are the instruments. So let's now have a look at the system in action. There's one behind me over on there. And what I'm going to do is just run through how we would do a VES measurement. Of course, it's on a desk. It just has a resistor attached to it. So the data that we're going to record won't be real, but you'll be able to see the workflow from that. So need to just double check that I am attached to the LS, to the Terrameter, sorry. So yeah, the Terrameter has a Wi-Fi network in it. My computer is currently connected to that Wi-Fi network. And I'm just going to use a piece of what we call VNC software. So this is some free VNC software. It's the kind of software that IT departments might use to remotely control your computer. And we're doing the same thing here. And Type VNC is a free version, and you can get this software for PCs, Macs, Android, iOS, Linux. Every kind of operating system will have some kind of VNC software that you can run. So all I'm doing is opening the VNC software and saying that I want to make a connection to this IP address, and that's shown on the front panel of the instrument. So I say connect. It'll ask me to put a password in, which is just guideline, nothing complex about that. And there we have the front panel of the instrument that is sat just behind me. So there's the IP address that I just typed in. I'll just make this a little bit bigger. Now, we're using the same user software for both the VES and the LS2. And the reason for that is that if you end up as a company having both a VES instrument and an LS2 instrument, we didn't want it to be a confusing state where you start one of the instruments and you're thinking about the software on the other instrument. So they actually use exactly the same user interface. The menu structure is all the same, so that no matter which of those instruments you've picked up, you'll intuitively know, oh, yeah, this menu, that menu, here's my measurement. So everything will look the same. So here I am on the on the home screen. This is where the instrument loads into. And what you'll see is that we have a series of tabs across the top, and those tabs change as we move through the measurement process. So I can either use the tab button, which is these two squares here. It suggests, that you're moving from one of these tabs to another, to jump to the next one, which is my project list, or I can use the arrow keys on the front and the OK button to show my list of projects. So you see I've moved across one tab now. So if I wanted to set up a measurement, I would create a new project, and that's just a folder to put a bunch of measurements in. Once it's created that project, in this instance, project number 4, it moves me across one tab, and now I can create a task. So a task is a single VES sounding or a borehole log or an ERT project if I was using an imaging system. So create a new task. It will bring up a window where it asks me, okay, what cable setup are you using? So I'm doing a VES measurement where I use the C1, C2, P1 and P2 connections on the end of the instrument. And I am going to do a Schlumberger measurement. Electrode spacing is grayed out because we don't have a fixed electrode spacing for a VES measurement. So say OK. And this will then jump directly to the settings pages. So you see the tabs have changed along the top. And because I am lazy, I will not set up my own settings. I will choose some from a list. So I'm in a 50 Hertz region. I want to do a resistivity and an IP measurement, and I want to use the 100% duty cycle, and I want a 1 second long measurement. So just press OK. That has now changed all of the settings to match that particular configuration. So those are my receiver settings. These are my transmitter settings. Now these ones I'm going to change because, as I say, I'm just operating with a small resistor attached to the instrument. So I don't want to blow that up. And I'm going to just switch off the electrode test because I don't have any electrodes attached to the instrument to test. The next tab along are our IP windows. So the way that we measure IP is we have a number of time windows and we measure how the voltage changes through those windows. Again, preloaded, and we would always recommend just using the preloaded settings for those. And if I was to do a borehole measurement, then I have the option to choose which parameters I'm measuring within the borehole and whether I'm measuring them when the probe is on its way down or when the probe is on its way back up. But we're not doing that for now. So my settings are done. I'm quite happy with those. And so now I would jump to do a measurement. So I just press the play button on the front panel of the instrument. And that jumps me directly to the measurement screen. And what you can see is that I have two options. I can either start the measurement straight away, or I can choose the electrode layout that I want to use. So at the moment, it's saying that MN/2. So MN/2 would be half the distance between the potential pairs. So i.e. the distance from the center of my spread out to the first potential electrode. So 0.2 meters. So from the center, 0.2 and 0.2. And then the current injectors are going to be 1 meter away. So from the center, 1 meter, from the center, 1 meter. So I can either put my electrodes out to that spacing and then start measuring, or I can jump through the different settings that are in that preloaded measurement script. And you can see that as I go through those, I'm changing the voltage spacing, and every now and again, the potential spacing changes as well. If I want to review that entire list, then I can move through the tabs till I get to the electrode positions page. And here then we can see the full list. And we have these preloaded ones, which are based on the kind of theoretical best case set of spacings based on how resolution decreases with depth. But you're more than welcome to go in and create your own electrode position in here. So you would just type in any number that you wanted for your A and B positions, and just come down here and say OK. and it would add that into the list. And then I would have the option to save that into a new list. So I could save that with a custom name. So I could just say that that was demo 1, save that. And then next time when I go into creating a task, that'll be one of the options as a measurement protocol. So choose my my first one there, and then go back to the measurement page. So I'm going to say start measurement. Gives me a warning to make sure there's no one touching the electrodes at this point. Say OK. And it will begin the measurement. Now, if I move one tab to the right, then I'll get the live results page. And this is the one that I would normally be watching during a measurement. This is the one that gives me plenty of information to know whether or not I'm collecting good quality data or not. So there we go. It's done its measurement. So current was being injected between C1 and C2 on the end panel. It was outputting just short of 100 milliamps. That current was completely fixed. There's no variation. Standard deviation is basically 0 on that. And it was pushing that through my little resistor with 550 millivolts. And that voltage didn't change either. So we're quite happy that the output, nice and stable, particularly the current. It's a constant current instrument. So we want that to be very, very stable. Then we look at our measured voltage. So it tells me that this was being measured between P1 and P2. It tells me what the voltage was. It tells me how much that varied. Well, it varied a fair amount because we're just using a little resistor strung across the instrument. Normally, we would expect to see that well below 1%. And if we do, then we're happy that we've got good quality data. We've done 4 stacks, 4 repetitions to improve the data quality. And then that equates to a resistance of 2.76 milliohms. So that is basically just taking the current and the voltage and using Ohm's law. That can then be converted to an apparent resistivity, and that is the raw data that would go into our sounding curve. Apparent resistivity against pseudo depth. We were also measuring IP, so we get a chargeability value. But again, these are terrible random numbers because the system is just sat on my desk at the moment. So once we've collected that first data set, then we can go back to our measurement screen. It says that there are currently no data points to measure because I have already done this first position. So I can just move now to the next one and I can start the new measurement. So say OK. And it will go through the same process. And we would, again, just quickly review the live result, make sure that this was a good data set. And then we'd be ready to move on to the next location. Now, the numbers are going to look fairly similar because, again, it's just working off the desk. If I move in the opposite direction, then I'll start to see my sounding curve build up. And every time you change the voltage spacing, the P1, P2 spacing, the icon changes for the points. So these will then become little crosses. And then when you change again, they'll go back to being triangles. Change again, they go to crosses. So you can always very easily identify which data points are associated with a particular voltage spacing. If I move again, then I have my table of results. And so that is showing me the reviewable list, and it always has the most recent measurement at the top. So it will show me the electrode positions, the measured voltage, how much that voltage varied during the measurement cycle, and that's the key one to knowing that we've collected good quality data, the apparent resistivity and the apparent chargeability. And then if we move one more, then we get back to that list of positions that we can choose from or create our own measurement value from. So very simple, very straightforward. Quite often you'll be using the same settings. So it's literally a case of switch the instrument on, create a new task, go to the measurement page and begin. So just quickly to close off here, we're going to talk about how we choose the right solution. And there are 3 options if you want to do VES. You can either have the Terrameter VES unit, the VES Max, or you could just go into the basic bottom end of the imaging systems and start with one of those to fulfill your VES needs, because of course those imaging systems can also do VES. Decision-making process would be, well, if you need to go deeper, then you'd require more power, more output voltage, more output current. So then you would want to be looking at something beyond the VES. So either one of the LS2, one of the imaging products, or the VES Max with its full current, full voltage. If you were wanting to do IP, then you would probably want the better recording circuits, and again, the ability to put more current into the ground. So again, you'd move sort of down this little diagram into either one of the imaging products or the VES Max. If you are thinking that you want to gradually move into ERT, where as your budget allows, you might want to start with a VES instrument because it's a lower investment and then move on to ERT later. Well, in that case, then the lower investment is on the left-hand side and the higher investment is towards the right. And the ease with which you can upgrade the instruments increases as you go from left to right. So with a VES, that needs to be sent back, have hardware put into it. But if you were buying a basic LS2 imaging system, then all upgrades for that can be done remotely. So horses for courses, I think, is the phrase that we use. And if you are interested, and obviously we'd be more than happy to discuss your particular requirements and which of those options we think would be best for you. And because this always comes up in webinars, price, just to be clear about where we're sitting this instrument right now, the VES will be sold for the rest of this year at the same price as the SAS 1000. And then the VES Max will be sold for the rest of this year at the same price as the LS2 VES used to be sold at. So we think that certainly for the VES, that's a very affordable point for the system that you're buying. And so if you want a quote or would like to just discuss more about the particular options that are available, then either contact myself, go through our website, use the contact form, or if you know your local Guideline Geo distributor, then please go and talk to them about it. Thank you very much. Okay, I'm going to move on to the questions. I saw a few popping in while I was talking, so I'll do my best to answer those, and I'll start with the one that was asked first. It says, can we do borehole IP survey by keeping receiver line potential electrodes over the surface and the current electrodes in the borehole? Yes, you could. That would be possible. There's no real limit in terms of how we set the instrument up, what the geometry of the electrodes. So we can tell the instrument where each electrode is positioned. So you could do that quite simply. Yes, is the answer to that one. Can we do, oh, that's the same question. It's just popped in twice. I think the system is glitched. Next question, can Terrameter VES be used with more than 16 electrodes using an external electrode selector device? Yes, it can. So I think you probably asked that just before I got to the accessories section. So what we said was ES1064 basically gives you that full imaging capability. The downside of using it with a VES instrument is that if it's the VES, you only have one measurement channel. And if it's the VES Max, you still only have two measurement channels. Typical ERT survey might have anything from 600 to 1500 measurements required to complete it. So if you have a VES, that means you need to inject current 1500 times in order to get the 1500 voltage readings. So that is A, very slow, and B, quite demanding on a battery. More channels you have, quicker you'll be able to complete a survey, and the fewer number of current injections you require, and therefore the lower your power budget. And that was the last question. So thank you very much, everyone, for attending, and I hope to see you in another webinar very soon. Thank you.